Welcome to Sketchy. We take all the super complex stuff you need to learn and turn them into memorable visual stories packed full of everything you need to know on test day. Click the link in the corner or description to try for free for 7 days. Now let's get to it.
Let's walk through how we'd balance this reaction, assuming it's happening in acidic aqueous solution. We'll look at one half reaction at a time so that we're not jumping back and forth between equations. But when you're balancing reactions on your own, it's totally fine, and sometimes even faster, to work with both half reactions at once. The first half reaction describes the reduction of chromium, whose oxidation number is changing from +6 on the left to +3 on the right, so it gained electrons. This means dichromate is actually the oxidizing agent in this case. And obviously, oxygen isn't balanced here, but we'll ignore that for now. But we do need to balance chromium, so make the product 2 chromium ions. And now we'll deal with those imbalanced oxygen atoms by adding 7 H2O molecules in the product to balance the 7 oxygens in dichromate. That's okay, even though water wasn't in the original equation because we're working with an aqueous solution, so we know there's water present to allow this. But that creates an imbalance of hydrogen atoms, with 14 on the product side and none on the reactant side. So we'll also add 14 hydrogen ions to the reactants. Remember, we can only do this step because we're dealing with an acidic solution, which by definition contains an abundance of hydrogen ions. Now that our atoms are balanced, we need to count out the charges on each side of the half reaction to balance those. The left side is +14 minus 2, so +12. The right is +3 times 2, so +6. Since the reactant side is more positive, we need to add some electrons there to even things out. 6 will do the trick. And now both sides have a total charge of +6. We'll pause there with the reduction half reaction and take a look at the oxidation half. This one's easy because sulfur is already balanced with 1 on each side. This means we don't need to add any coefficients and we can get straight to balancing oxygen. There are 3 oxygen atoms on the left and 4 on the right, so we'll add 1 molecule of H2O to the reactants to balance these. That makes 2 hydrogen atoms on the left and none on the right, so we'll also add 2 hydrogen ions to the product to balance the hydrogen atoms. Now, to count up the charges. It's 2- on the reactant side from sulfite. Then on the product side, the 2- from sulfate is cancelled out by the 2 hydrogen ions for a total charge of 0, which means we need to add 2 electrons to the right side. Okay, now that both half reactions are balanced in atoms and charge, we need to balance the total number of electrons transferred when you bring it all together. In the first half reaction, 6 electrons were transferred. In the second, there were only 2. We can't bring these half reactions together yet because if the reaction started with more electrons than it ended with, we wouldn't have conservation of charge. So we need to multiply each component of that second half reaction by 3 so that it also ends up yielding 6 electrons. And voila! Now all things are equal, so we can bring it all together to form a single redox equation. Now, all that's left to do is cancel out anything that appears on both sides. If you've done things right, the electrons should always cancel out altogether and disappear from the equation. For other components, you'll often be able to remove them from one side of the equation, then adjust the coefficient on the other side to account for how many cancel out. And there it is. We've got our simplified, balanced redox equation.